Welcome to this next lecture. In the previous lecture, we have looked at all these basic concepts related to diffusion and reaction. We have looked at Thiele modulus, Weiss-Prater criteria, Mayer's criteria. All those criteria we have defined. We have seen their meaning. We have seen why they are useful. Now we will start using all of these in some problems. So just before we get started with this lecture, let me just show you where we are with respect to our course. We are on part 5 of our course, solid catalyzed reactions, diffusion and reaction in porous catalyst. We have looked at this. We have looked at external and internal mass transfer resistances. We'll look at heat transfer resistance later on, but let's focus on design aspects in this class. Just to help you to revise, what is the physical significance of Thiele modulus, effectiveness factor, Weiss-Prater criteria or Weiss-Prater number if you like, Mayer's criteria. How is the effectiveness factor related to Thiele modulus? Write an expression for overall rate of reaction per unit volume of the catalyst considering all the transport and kinetic limitations. So if you revise, if you answer these questions, it will be an automatic revision of all the lectures, all the previous lecture that was there. Then you can better appreciate what is going to come in this lecture. So here is a problem. So this is one problem. Nitric oxide plays a role in smog formation and therefore is a pollutant which needs to be removed. It is proposed to reduce this concentration of nitric oxide from an effluent airstream by passing it through a packed bed of spherical porous carbonaceous spherical particles. Feed mixture contains 20,000 ppm by moles of nitric oxide in air at a flow rate of 0.1 meter cube per hour through a 2-inch ID tube packed with porous solid at the temperature of 1173 Kelvin and a pressure of 1 atmosphere absolute. NO reacts with carbon to form nitrogen and carbon monoxide. Assume that the amount of carbon is far in excess so that the solid phase properties essentially remain unchanged. The rate of reaction on the surface of the carbon is K 4.42 into 10 raised to minus 10 second inverse. Calculate the mass of carbon required to remove 99.9% of the NO from the mixture. Assume that the amount of carbon is far large. So we are going to treat as if the carbon is actually the carbon is reacting, but because its mass is so large, we are going to treat as if the carbon is far in excess. Far in excess, as if it is like a catalyst particle. Right? Okay. Draw a schematic to visualize the problem better and then solve. Pause and solve for yourself. Here's the solution. Okay, so this is like your packed bed. There is a carbon that is there. These, you can imagine that these are all carbon particles if you like. We are going to take a small differential element dz, Qg is the flow rate, let's say. So assume that gas flow rate, because it's a dilute mixture, nitric oxide is only in ppm level, so the gas flow rate and pressure and temperature are going to remain the same. So now if you define Ra in terms of per unit weight of catalyst, then we can write this balance minus Qg dCAB would be equal to Ra into dV if Ra is in terms of per unit reactor volume, or if it is in terms of per unit weight of catalyst. You see how defining different things, how defining the rate differently allows you to calculate different things. Okay, so now if you consider external mass transfer as well as pore diffusion and kinetics, this is our rate expression we saw at the end of the previous lecture. So rate per unit weight of catalyst, this is per unit volume of catalyst. So rate per unit weight of catalyst would be this expression divided by rho p. This would be per unit weight of catalyst, you see. So I need to estimate Kf, I need to estimate A bar, I need to calculate eta. Then only I can integrate and get a weight of the catalyst. Do you agree? So estimate for yourself, pause and do it for yourself, then go forward. Okay, so to estimate eta, first of all, we need the Thiele modulus. How do we get Thiele modulus? Ks is 4.42 into 10 raised to minus 10 meter per second. So this is based on per unit surface area of the pores inside. Right? So if catalyst properties are, let's say, catalyst means carbon properties. We are treating, because carbon is far excess, we are treating as if it is not changing at all, it behaves like a catalyst. So S is 500 meter square per gram, rho P is say 1500 kg per meter cube. So then K would be so many meters per second into meter square per kilogram. 500 meter square per gram multiplied by 1000 would be meter square per kilogram multiplied by rho P. Kg would cancel, meter cube will cancel. Then this K would be per unit volume of the catalyst. So effectiveness factor would be square root K effective diffusivity divided by L. So we need effective diffusivity. So assume that effective diffusivity is like 10 raised to minus 6 meter square per second. Just assume right now. And catalyst is spherical. So R is equal to 3. So phi would be square root K diffusivity. L is now R by 3. 3 millimeter radius. So 3 by 3, 1 millimeter. Take care of units. Effective diffusivity in meter square per second. R is in millimeters. So phi would be 0.576 and eta would be 0.902. Now we need to estimate external mass transfer coefficient Kf. I need velocity. So to get Kf we need Sherwood number. Sherwood number depends on Reynolds number and Schmidt number. To get Reynolds number we will need velocity. So velocity 0.1 is meter cube per hour. Recall 0.1 meter cube per hour. Divided by 3600. Cross section pi by 4 d square. 2-inch inner diameter. 2 inches is like 5 centimeters. So 0.05 square. So velocity is 0.014 meter per second. So this equation if I use for Sherwood number, this is there in Fogler's book. If you've read the chapter which I had assigned to you last time, you will get this expression. This is our Sherwood number is equal to Reynolds number into Schmidt number. So Reynolds number is 2.5. What is the Reynolds number? U velocity, dp particle size, rho of the fluid, 1 minus epsilon, mu of the fluid. So if I assume ideal gas law, rho would be Pm by RT, and because majority of it is air, molecular weight would be 28.84. So rho 1 atmosphere Pm by RT 1173 Kelvin. Rho would be 0.3 kg per meter cube. Rho of the fluid, air in this particular case. Let's assume that molecular diffusivity in the bulk of the gas is 10 raised to minus 5. 10 raised to minus 6 is effective diffusivity inside the catalyst or inside the carbon. This is bulk diffusivity. So Reynolds number would be 0.014, 006, diameter is 6 millimeter, 0.3 rho f mu epsilon. Reynolds number would be 5.076. Schmidt number would be mu divided by rho and bulk diffusivity 3.33. That decides the external mass transfer thickness of the film. That's the importance of Schmidt number. Recall momentum boundary layer thickness and concentration boundary layer thickness. Undergraduate course, Schmidt number. So if you substitute here, Sherwood number would be 3.36 and mass transfer coefficient would be 0.0056. A surface area would be external surface area. It is not the pore area now. We are defining external mass transfer. So external surface area is 6 divided by dp. It is 1000 meter square per meter cube of the catalyst. So KFA would be 5.6. This will have units of per second. Per second. Okay. Same way, this K has units now of per second. Now we can use this K. We can use this KFA in and eta in this expression. You see, and solve this equation. Do that. So 1 by KFA is 1 by 5.6, 0.1786. This is like mass transfer resistance. 1 by eta K 0.902, 0.3315 is 3.34. So mass transfer resistance is through the pore. Diffusion resistance through the pore is large as compared to the external mass transfer resistance. See, it is 20 times larger. So essentially reaction is controlled by pore diffusion plus reaction. Pore diffusion also is small because effectiveness factor is 0.9. Essentially, it is reaction controlling, but practically kinetically controlled. Substitute RAW would be CAB rho P divided by 1 by KFA 1 by eta K. Substitute. You'll get 1.89 into 10 raised to minus 4 Ca bulk. Now this is per unit weight of catalyst. So minus Qg divided into dCA by into dCAB is 1.89 into 10 raised to minus 4 CAB into dW. Right? Simplify. You will get Qg, Ln, and so on. W. So now you can calculate W. 10.1 kilograms of catalyst. What is the volume of catalyst? 10.1 kilograms would be 0.0067 meter cube. If reactor volume is 0.067, reactor is now catalyst is packed inside this reactor tube. So voidage comes into picture. So reactor volume would be 0.00676 divided by 0.5. That's 0.0135 meters cube. So if diameter is 5 centimeter, length would be 6.9 meters. This is how we would use all these considerations, all these concepts for calculating reactor sizes, calculating weight of catalyst needed. This is how we are going to use. Understand all this, then only go forward. Okay, little bit about residence time. So this weight of catalyst divided by this Qg, I can define this like a residence time. Okay, or Qg divided by weight I can write. It will be like velocity. If you define in terms of volume, let's go back a little bit. Yeah. So Qg, gas flow rate, and this volume, this is like residence time, or Qg divided by, if I define volume as cross-sectional area multiplied by height, then this Qg divided by S would be like velocity through the bed, velocity through the reactor. So this Qg and volume or Qg and weight, we can define in terms of residence time, we can define in terms of velocity. So there are different ways in which we calculate for catalytic reaction, or weight, different ways in which we define. For catalytic reactions, rather than defining residence time, we define space velocity. Space velocity is either for the liquid hourly space velocity or gas hourly space velocity. So this is LHSP if you want. It is liquid volumetric flow rate per hour divided by catalyst volume. So this is like Qg, liquid flow rate, QL, divided by volume of the catalyst. Gas hourly space velocity is the volumetric flow rate of gas divided by volume of catalyst. So this is like inverse of residence time. Do you see that? Or we could, rather than defining based on catalyst volume, we could define based on weight. Then it will be weight hourly mass space velocity. So this would be mass flow rate of gas, kg per hour of gas, divided by kg of catalyst, or mass flow rate of liquid, kg per hour of liquid flow, divided by kg of catalyst. So it will have units of 1 per hour. Then this is like our inverse of this is like our residence time, but now in terms of weights, not in terms of actual contact time. Actual contact time is like this. So this accounts for density of the gas and density of the catalyst, right? They are interrelated, they can be interrelated based on the density of catalyst and density of the gas. You see that? So this is how we would define, this is how people define contact time or residence time in terms of their inverse, in terms of velocities. Just for information, because there is sometimes values are given in terms of this. So I want you to define, or I want you to decide on what parameters and operating conditions that will influence the rate constant, effectiveness factor, mass transfer coefficient, and surface area, and plot qualitatively how these parameters affect the overall rate of reaction. This is our overall rate of reaction. So what parameters would affect rate constant? One could be surface area, second could be number of active sites, third could be temperature. What parameters would affect effectiveness factor? Means now Thiele modulus, effective diffusivity, size of the catalyst, rate constant. What parameters would affect mass transfer coefficient Kf? It would be turbulence, means velocity, Reynolds number, Schmidt number. What parameter would affect interfacial area? Surface area. This is surface area, external surface area per unit volume. This would be affected by size. So I want you to plot qualitatively how these parameters affect the rate of reaction. Now based upon this, think about how would you determine intrinsic kinetics of a fluid solid catalytic reaction. Intrinsic means actual rate constant, which is not observed actually. What would is the rate constant? Because actually it might be limited by external mass transfer, actually it might be limited by pore diffusion. So I wanted to think about how we could determine intrinsic kinetics of a fluid solid reaction. So when we say intrinsic kinetics, determine intrinsic kinetics, what we mean is how do I determine intrinsic rate constant K, order of reaction N, and energy of activation. We've seen this in our undergraduate. What do we mean by kinetics? Let me just give you some examples. You do this for yourself. The lecturer does not have this solution. I'm just going to give you one possibility. So if I say surface area, external surface area. So if I increase external, if external surface area is very small, what would happen? Kf would be very small. If Kfa is very small, what would mean? Mass transfer is limiting. External mass transfer is limiting. Then Ra will increase with A bar. But as A bar goes up, external mass transfer coefficient becomes, or overall volumetric mass transfer coefficient becomes larger and larger. External mass transfer resistance becomes limited, less and less. This contribution becomes less and less. Then rate approaches some constant value independent of A bar. So here reaction is mass transfer limited. Here reaction is pore diffusion and kinetically limited. Okay. And in terms of external surface area, we can think about this as 1 by dp. So if you plot Ra with respect to dp, how will it look like? Exactly opposite of this. For small dp, there is no external mass transfer resistance, but for large dp, there is external mass transfer resistance. So this is external mass transfer limited. This is not external mass transfer limited. Think about this. Like this, plot graphs for every parameter that you have listed here. Every parameter that you have listed here. Every parameter that listed here. And then think about how do I determine kinetics. Do this for yourself. Then you will understand all these things. Let's go forward. So if I have to determine kinetics, I need to ensure that external mass transfer resistances are eliminated. But what about pore diffusion limitations? So suppose I say nth order reaction that is limited by pore diffusion. We would have Ra would be eta would be 1 by 5 K CAS raised to N. And then we can write this as K diffusivity. The Thiele modulus I can replace diffusivity root K CAS raised to N minus 1 L K and CAS raised to N. So Ra would be root effective diffusivity root Ka CAS raised to N plus 1 by 2. Get this for yourself. Get this expression for yourself. That means Ra would be proportional to root K naught exponent of minus E by RT Cas raised to N by 2. Now if the reaction is limited by pore diffusion and we vary CAS and see how rate changes to get the order of reaction, we will find that order is n plus 1 by 2. It's an apparent order. It is m plus 1 by 2. Nm is equal to n plus 1 by 2. Apparent order is n plus 1 by 2. Actual order is 2 times apparent order minus 1. We are falsely getting a dependence. This is our apparent order. So therefore it is called as falsified kinetics. Falsified kinetic. That's the title of the slide. Same way, if I vary temperature to and see how rate changes, what we will find is the apparent activation energy is E by 2. Actual activation energy is double of our apparent activation energy. So if I do measurements, varies concentration and get the order, vary temperature and get energy of activation, we are going to get false information. What is the false information? Apparent order. Actual order is different from apparent order. Actual energy of activation is different from apparent activation energy, right? So we need to ensure that even when we are measuring kinetics, even the internal mass transfer or pore diffusion limitations are eliminated. Think about how we are going to do this. Okay. Suppose we are limited by external mass transfer. What we will find? We will find that the order is 1. That may not be correct. It's false. False information. If we vary temperature, we'll get a dependence of Kf on temperature. Kf varies with temperature very little, very weakly. Energy of activation is 3 to 5 kilocalories per gram. We can use this information to determine which regime we are in as well. So if you plot ln Ra versus 1 by T, if reaction is kinetically controlled, then energy of activation will come out to be more than 10 kilocalories per gram. If we are limited by external mass transfer limitation, apparent activation energy would be 1 to 3 kilocalorie per gram. So if I measure, other way of looking at it is if I measure energy of activation and the energy of activation happens to be in this range, we know that it will be external mass transfer control. If I measure energy of activation and we find that energy of activation is in this range, we can conclude that we are in a pore diffusion limited regime. If energy of activation is more than 10 kilocalories per gram mole, then we can say, we are in a kinetically controlled regime. So these falsified kinetics we can use and check what is the apparent activation energy. Is it like this? Is it like this? Is it like this? Then we can conclude whether it is we are in an external mass transfer control regime or pore diffusion control regime or kinetically controlled regime. Think about all these things. This rate versus temperature, this is our experimental observation. We can do an experiment and find out. And get apparent activation energy. Think about all these things. So one way of doing that is to do experiments in a packed bed reactor, right? In packed bed reactor, we need to eliminate pore diffusion limitation and we need to eliminate external mass transfer concentration limitations. How do you eliminate external mass transfer? Increase turbulence, increase gas velocity. So if you plot rate versus gas velocity or liquid velocity, if it's a liquid catalyzed reaction, how do you think it will look like? At low liquid velocities, it is limited by external mass transfer, so you will have a linear variation. But at large velocities, you will not have external mass transfer limitation. Same way, I can reduce the particle size. By reducing particle size, we can reduce Thiele modulus and we can increase effectiveness factor. Get away from mass transfer, external pore diffusion limitations. So if I plot rate versus dP, we have seen this earlier. At small dP, there is no mass transfer limit, pore diffusion limitation. At large dP, there is mass transfer, pore diffusion limitation, internal mass transfer or pore diffusion limitation. Think. This is how it will look like. I can rub out this. Now I have drawn. Think. So we do experiments at large enough gas velocity so that we are in this regime. We do experiments at small enough particle size so that we are in this regime, and then we can vary concentration of reactant and get order. Then we can vary temperature and get the actual energy of activation. This could be a setup. You could have a liquid, vaporized, gas going through, catalyst is there, heater is there, beads are there just to make sure that heat is transferred so that we can vary temperature, and then whatever gas comes out we can condense that. There will be a gas and liquid can be separated. So this is experimental setup, possibility of one possible experimental setup that you can make. Another possibility of reducing or eliminating gas side resistance is to have a packed bed with agitation or a spinning basket reactor. This is called as a Berti reactor. There is a basket in which catalyst is there and there is an agitator which increases the turbulence. Or there is a basket with catalyst filled inside and this whole basket rotates at different speeds. These are called as Carberry reactors. So if you are talking about Berti reactor, plot rate versus RPM. How will it look like? At small RPM, we are external mass transfer limited. So rate increases with external mass transfer, rate increases with RPM. And beyond a certain RPM, we will be not limited by external mass transfer. Right? Not so in this regime, not limited by external mass transfer. I can take this basket and fill it with different particle sizes. Same again like last time. Small particle sizes, the rate is not limited by pore diffusion. Large particle sizes, the rate is limited by pore diffusion. Not limited by pore diffusion. So when we want to do experiments, beyond this RPM and below this particle size. That's where we should do our experiments so that we can get intrinsic kinetics. We will not be limited by diffusion, either external or internal. I've written it now, so let me just rub out all these things. Understand all these, then only go forward. Understand what we are saying. Here is the problem. Vapor phase dehydrogenation of glycerol to acrolein at 1 atmosphere is studied in the experimental setup shown. So glycerol is taken here, aqueous solution of glycerol is taken here. It is put through a vaporizer, so you get a vapors of aqueous solution of glycerol. So which means you have water vapor and glycerol vapors. You are using nitrogen gas just to dilute. It is going through this bed. Beads are just to transfer heat from the heater furnace, so that when it sees the catalyst, it is at a temperature that we want. We are measuring the temperature as well. Thermocouple I have not shown. And then once you get glycerol reacts, you get acrolein. Water is already there. You condense that. Nitrogen goes out. Acrolein and water and unreacted glycerol come as a liquid. This is the experimental setup. This is glycerol, acrolein. Water is generated in the process. Dehydration. So I'm going to give you some data on this. I'm going to give you some data on this experimental data for this reaction, and then I'm going to ask some questions. So you can read, pause and read the problem statement. Once you have read, made notes, then go forward. Here is the experimental data. 1 gram of catalyst, 20% by weight aqueous solution of glycerol here. Feeding rate ml per hour. Feeding rate ml per hour. Right? So 10.2 ml per hour. Glycerol weight percent is either 10% by weight, 20% by weight, or 50% by weight. Aqueous solution of glycerol is here. Flow rate is 10.2 ml per hour here. Liquid fed. Liquid fed. Liquid flow rate. It is before the vaporizer. 10.2 ml per hour. Obviously, vapor volume will increase. Nitrogen flow rate. Standard liter per hour. Standard liter per hour means liter per hour measured at 1 atmosphere and 0 degrees centigrade. 1.5, 0.75, 1.5. So this is the nitrogen flow rate. 0.75, 1, 1.5, 3 standard liter per minute. Take care of units, huh? This is liter per hour. This is ml per hour. Okay. Temperature in the reaction. Temperature 275, 300. That's the temperature. 325. Okay. And what is going to be, what is told is conversion of glycerol, percent conversion of glycerol. Percent conversion of glycerol across the catalyst, right? What comes in minus what goes out. It is either 86% converted, 92% converted, 96%. So this is the experimental data. Somebody has done experiments and got this data. Now I'm asking you questions. 1 is calculate rate of reaction of glycerol on the catalyst surface in terms of kilomoles per second per meter cube of catalyst. So we want rate in terms of per unit volume of catalyst. Okay. I want you to calculate inlet, outlet and average concentration of glycerol in the reactor. Inlet, outlet and average concentration of glycerol. Check if external mass transfer is limiting. Check if reaction is kinetically controlled. Rate constant, order and energy of activation. Calculate all these things. Calculate all these things. Use all the concepts in this lecture and the previous lecture to calculate. Use all the concepts in this lecture and previous lecture to calculate. You do for yourself. Don't go forward. Pause and do these calculations. Then only go forward. The last column tells you percent concentration of glycerol. It is hidden behind the camera. Read the statement. Do this for yourself. Okay, one way is to do it, use a spreadsheet and calculate all these things. Put this data in an Excel spreadsheet and calculate. I'm just going to give you some solution. Here are some more data if you like, just to help you. Some data. Assume viscosity is 10 raised to minus 5 for the gas mixture. Diffusivity of glycerol in glass is 10 raised to minus 5. Assume that aqueous glycerol has a density of 1.1 gram per centimeter cube. Since so much inerts are present, water and nitrogen we can assume that the volumetric flow rate of the gas mixture does not change significantly even when glycerol is reacting. Note that SLPH means standard liter per hour gas volume measured at 0 degrees 1 atmosphere. And assume ideal gas law to be applicable because it's at 1 atmosphere and high enough pressure, high enough temperature. Temperature is 275, 300, 325. Solve for yourself. Here is some solution. You want hints? Use a spreadsheet. Convert the data into molar flow rates, concentrations, calculate rate based on change in concentration, calculate external mass transfer coefficient, determine energy of activation, determine order, think whether the order and activation energy represent falsified kinetics. Think. Here's the solution. If you have not done it, pause. Okay, so for every case, weight percent, liquid flow rate, nitrogen flow rate, temperature, conversion of glycerol, this data is given. Right? Temperature we can convert to Kelvin. Mass flow rate solution, density per hour is given, density is given, we can calculate grams per hour. Weight percent of glycerol is given. So these many grams per hour of solution is fed, we can convert to glycerol grams per hour, water grams per hour. We can calculate glycerol molar flow rate, water molar flow rate. Nitrogen LPH is given. We can calculate nitrogen molar flow rate. So total molar flow rate we can calculate at the entry of reactor. And using the total molar flow rate, temperature and pressure, 1 atmosphere, use ideal gas law, we can calculate the volumetric flow rate. So what have we got now? What have we got so far? We have got volumetric flow rate entering here. We have got molar flow rate entering here. We have got glycerol moles molar flow rate here. So we have got inlet glycerol concentration. See, this total volumetric flow rate and glycerol molar flow rate will tell you gram moles. If you divide this by this, you will get gram moles per liter of glycerol concentration entering the catalyst bed. If you have not done it, pause and do it. Okay, glycerol molar gram mole per hour, this is there, we have calculated total gram mole per hour, we have calculated total molar flow rate, we have calculated. These two give us inlet glycerol concentration. We know conversion, so we can calculate exit gram mole per hour. So rate, this is now our observed rate. This is our R observed, you see. R observed would be glycerol flow rate, inlet, gram moles per hour multiplied by conversion. Will tell you how many gram moles per hour of glycerol are reacted. Divided by volume of catalyst. What is the volume of catalyst? We know 1 gram of catalyst, right? Divided by density of catalyst. Where is that gone? Right? Density of catalyst we can have I given to you. Yeah, probably it is here. Yeah, density of catalyst is here. We know how much volume of catalyst we have taken inside. So we can calculate observed rate. Gram moles of glycerol reacted per liter of catalyst per hour. See? What is the average concentration that the catalyst sees? It is average of inlet and exit. Average of these two. Now we want to find external mass transfer resistance. So gas velocity we can calculate, total molar, total volumetric flow rate we know. Divided by cross sectional area. Total gas velocity we know. This can be calculated. Gas density we can calculate. Ideal gas law. Reynolds number we can calculate. Schmidt number you can calculate. Sherwood number we can calculate. Mass transfer we can calculate. Mears criteria now we can calculate. Remember what was Mears criteria? R observed something. Go back and see your lecture and see. Right. What does this tell you? Mears criteria. Values are far less than 1. What does it mean? External mass transfer is not important. External mass transfer. When I say not important, means it is not limiting. It is not limiting. External mass transfer resistance is negligible. What about pore diffusion limitation? Can I calculate Weiss-Prater parameter? For that, I need effective diffusivity. Effective diffusivity we can calculate, right? If I know the pore size, we can calculate effective diffusivity. But porosity, tortuosity are not known. Can't do much. Then what do we do? Then how do I decide? Think. Pause. Don't go forward. Think and then see. One thing we can do is plot observed rate versus temperature. First three data points. Observed rate we know. Let me rub out this. Observed rate we know. At different temperatures. These three data if we take, these three data are at three different temperatures. 275, 300, 325. You see. We can plot ln r observed versus 1 by T. Right? And data from set 4 to 9, there are different concentrations. Set 4 to 9, they are at different glycerol concentrations. Why? Because the liquid flow rate is the same, but different nitrogen flow rates are there. That is what is changing the glycerol concentration. Data set 4 to 9, glycerol concentration is changing, you see. Inlet, outlet and average glycerol concentration is changing. So if you plot ln rate versus 1 by T, ln r observed, slope, what is the slope? This is the slope. ln rate versus ln Ca average, what is the slope? This is the slope. What does it tell you? What does it tell you? What do we conclude? Pause, conclude yourself. Don't wait for me. E by R is 790.17. 790.17. So E is 1.6 kilocalories per gram mole. This is very low. What does it tell you? Means you are likely to be diffusion limited, internal diffusion limited, rather than kinetically controlled. So kinetics are likely to be falsified. Apparent order is 0.456. 0.4559 means 0.456. So what is the actual order? N? What is that? What is the relationship between actual order and apparent order? Go back to lecture. See for yourself. Actual order. Two times apparent order minus 1. Two times 0.456 minus 1. Right? This is like 0.9 minus 0.1. And nearly zero order. Nearly zero order means perhaps desorption of products is the rate controlling step. Desorption of products is rate controlling step. We can conclude all these things. Think about all the things that we have done. Think about it. Think about what conclusions we have made, how we have reached those conclusions. So homework. If you are following Fogler's book, 4th edition, chapter 11, chapter 12, problem 11.5, 11.11, problem 12.4, 12.5, 12.6, 12.16, 12.17. These 7 problems you try on your own. If you solve on your own, that will enforce your learning. You will be able to understand, comprehend all this material. You see how all these concepts we have used for analyzing a reactor, analyzing laboratory data, getting intrinsic kinetics, designing a reactor, what length of the bed would be required. Read this lecture or see this lecture again and again till you are comfortable with all the things that are talked about in this lecture. Without that, don't go forward. In the next lecture, we are going to look at heat transfer considerations. If reactions are exothermic, in so far in the last 2 lectures, we have not at all considered temperature effects. We have not at all considered that reaction is exothermic. We have only said rate constant is the same everywhere throughout the catalyst, as if reaction was isothermal. So think about now how we could write or how we could calculate all these things if the reactions were exothermic. We'll stop this lecture. That's what is going to come in the next lecture.